Okay, so we learned about the union of two sets. We also learned about the intersection, and we showed some properties of the intersection and the union of two sets. But for example, if I go to the previous theorem that we had, so if you remember, we had a theorem like this with 9 items. But if you see, for example, in this theorem, the operation that I have been using all the time is the intersection. For the similar theorem that we had for the union, you see again, all the operations that I have been using here is the union between two sets. But there are some relations that we can have both union and intersection in one formula. Okay, so I wanted to talk about those formulas today. So the first one I want to talk about is this distributive laws. Okay, so let me write the content. Let A, B, and C be sets. Then we have two formulas. These are called distributive laws. Yes, and one is A intersection with the union of two sets. So you see, this is the first time that I have both operations in one formula, intersection and union. If you want, you can distribute this inside this pair of brackets. So what I mean that you can write A intersection with B, and then you can write A intersection with C, and then union them. Okay, so this means that the intersection is distributive over the union. So I take A intersection, I distribute it here. So let me just give you an analogy and then I will clean it. For example, you know the multiplication and addition in numbers, yes? So you can write A dot B plus C, then you know that you can write it as A dot B plus A dot C, yes? In principle, we should have a pair of brackets around them, but because we have the convention that the product has the priority over addition, so the multiplication has priority over addition, this is why we don't usually put these pair of brackets, because by that convention, we usually do this one first, okay? Let me, by the way, check that this microphone is the correct microphone, yes. Okay, and then this is called, so this means that multiplication is distributive over addition. So I can take this A and distribute it inside this pair of brackets, which of course is a very elementary thing for you right now, yes? So, but of course, you know that this formula the other way around is not correct. So for example, if I ask you, can I distribute addition over multiplication? If it was right, then it means that you could write A plus B multiplied by A plus C. But of course, you know that this is not correct, yes? So this shows that multiplication is distributive over addition, but addition is not distributive over multiplication, because if it was, then this formula should be correct. But it is easy to convince yourself that this formula is not correct. For example, you can choose A equal to 1, B equal to 2, C equal to 3. When you calculate the left-hand side, it becomes 7. But when you calculate the right-hand side, it becomes 12. Yes, so they are not equal. So this just one single example shows that this formula in general is not correct, but we know that this formula is correct. So we say that multiplication is distributive over addition, but not the other way around. But when it comes to sets, both intersection is distributive over union, and the other way around. Union is also distributive over intersection. So this is why I have written distributive laws, because we have two of them. Okay, so let me clean this. We don't need this anymore. So number 2, I can write A union B intersection C. So how this will read, I can, according to this theorem, I can distribute a union inside this pair of brackets, and I can write A union B intersection A union C. Okay, let me write this once more here to compare. You see, here you have 2 operations. This is very familiar for you. You see, when you distribute, the operation that you use here and here is the operation that you have here. But the operation that you use between them is the operation that you have here. Both of them have this structure. You see, for example, in the first one, this operation is playing the role of this here now. And you see that between these 2 sets, between these 2, I have exactly this operation. So this operation is the same. And between these 2, I have this operation involved. And that's exactly the case. Between these 2, the operation that you see is the union, which is exactly this operation. By the way, from this direction to this direction is called distribution. But from this direction to that direction is also possible. This is factorization, yes? So in principle, you can factor an A out. That is also the same thing here. If you go from this direction to this direction, you say that I am distributing A intersection over the union. You can also, if you want to, go in the opposite direction because you have equality. So this means that it seems that I am factoring A intersection out. So when I factor A intersection out, from the set, first one B is left, from the second one C is left, and the operation between them is the union one. And the same thing for the second one. Okay. Any questions about this structure?
No.
Okay, good. But let me, for example, let us prove one of them, okay? I can prove the first one. Number 1. Here I am claiming that I don't know anything about these 3 sets. They can be any 3 sets, but I am claiming for any 3 sets, the left-hand side, which is a set, is equal to the right-hand side, which is also a set. So these 2 sets, I am claiming that these 2 sets are equal. So do you remember, if I want to show that 2 sets are equal, if I ask you, show that these 2 sets are equal, what you need to do is to show that whatever is an element of A is also an element of B and the other way around. And this means that A is equal to B. So here I want to show that these 2 sets are equal. I would say that let X be an element inside the left-hand side set. We show that X also belongs to the set on the right-hand side. Okay? And of course, the other way around. And the other way around. So let me, yeah. Yes? So how should I do that? Okay, now tell me, if I tell you that I found an element X inside this set, this implies what? You say that this X belongs to the intersection of this set and this set. So what does this mean? This means that X has to be in the first set and it has to be in the second set as well. Yes, that is the definition of the intersection. You are telling that X belongs to the intersection of these two sets. So definitely X is both in the first one and in the second one, and that is what I have written here. Okay, but now you say that X belongs to the union. What can I conclude from this? So I can conclude that, of course, you are telling me that X belongs to A, and X belongs to B union C means that X belongs to B or X belongs to C. That is the definition of the union. Yes? So there are two possibilities. I am sure that X belongs to A. This is guaranteed. But I am not sure that X belongs to B 100% because it might be in C. I am not sure that X belongs to C 100% because it might be in B. And of course, I told you that OR in mathematics is inclusive. So it means that it might happen that X is in both of them. But what is guaranteed for me is that X is in A. And what is guaranteed for me is that at least one of them is true. Okay, so this means that I can conclude that X belongs to A is guaranteed. If X belongs to A, then I will have this situation. If X really belongs to B, then I can say that, okay, X belongs to A and X belongs to B. Then I write it here. But if this is not true, there is only one possibility left, and that is that X belongs to A and X belongs to C. Yes? These are the only possible cases. So X belonging to A is 100% guaranteed, but at least one of them is true. So if this is true, because I also know this is true, then I know that both of them are true. But if this is not the case, then this one and the third one has to be true. And that is what I have written here. Now, if I ask you what you can conclude from here, someone tells you that X belongs to A and X belongs to B. So what can I conclude if this is the case? If this is the case, I can conclude that X belongs to A intersection B. Because if you say that X belongs to A and X belongs to B, this definitely implies that X belongs to A intersection B. But because you might say that this is not only the case, because there is another possibility, and that is this one, I would say that, okay, might be this happens or the other one happens. But when the other one happens, what does it mean? X belongs to A and simultaneously X belongs to C. So I can conclude that X belongs to A intersection C. Now you are telling me that you have an element. Either this one is true or that one is true. So it means that X belongs to this set, or if not, definitely it belongs to this set. So this means that definitely X belongs to the union of these two sets. Yes, A intersection B union A intersection C, because you are telling me that either X is in this set or it is in this set. So definitely it is guaranteed that X should belong to the union of these two sets. Yes? So this means that I took an arbitrary element from the set on the left-hand side, and by the definition of the union and intersection and a little bit of logic, I was able to show that that element also is an element of the right-hand side set. Of course, this doesn't guarantee that these two sets are equal. This only guarantees that whatever is inside here is also inside here. So this, in principle, this guarantees so far that this is a subset of this. Yes? But I want to show that they are equal. So it means that now I need to do the other way around. I need to take an element here and show that based on definition of intersection and the union and logic, I can conclude that that element belongs to this set as well. But instead of rewriting it again, let me change the color. You can convince yourself easily that this arrow is invertible, yes? Because if someone tells me that X belongs to this union, then I can immediately conclude that this X is either in the first one or in the second one. So this means that I can come back to this. But now, if someone tells me that X is here or X is there, I can also conclude back, yes, because that is exactly the definition of intersection. When you say that X belongs to intersection, I can immediately conclude this statement if I want to. And if you say X belongs to A intersection C, I can conclude this one. So now I can also go back from this statement to the previous one, because what you are saying here, if you see X belonging to A is 100% guaranteed, but I am doubtful about X belonging to B or X belonging to C. So this means that X belonging to A is definite, but either X belongs to B or X belongs to C. So this means that this is also a reversible. And then the final statement is clearly reversible, and that one is also reversible. So it means that what element on the left-hand side set, I was able to show that that element is on the right-hand side set, and whatever is inside the right-hand side set, it is also in the left-hand side set. So this means that they are composed of exactly the same elements, and this means that they are equal. So that is a mathematical rigorous proof of this. You can just take the second one as an exercise yourself. Any questions regarding this proof? Okay. Now there are some other exercises in the book related to this relation. So, for example, let me also mention those things. So, example. So I would say let A, for example, be the set containing of A, B, C, D, E, and F. B be another set, for example, A, E, and F. And C be a set E, F, and D. So I would say investigate the validity of the previous theorem. Of course, this is not a mathematical proof, but this investigation shows that at least for these three sets, these are valid. So that is just a good exercise to understand what's going on intuitively or in a simpler context, yes? Okay, in these kinds of, I will do the first one and then you can do the second one yourself, okay? So if this question is given, there are questions of this type in the book. They are very easy. So the sets are given to you. What you need to do, you need to take these sets and determine the left-hand side. You take these sets and determine the right-hand side, and at the end you compare them. They have to be equal, yes? So the way that you need to write it, I would say that if I want to solve number one, for example, number two, you can do it as an exercise yourself. So the left-hand side, which is A intersection B union C, you need to write it properly. So instead of set A, I plug what is given to me, and this is this set. And after that, you see after A, I have intersection, and then I have a pair of brackets. Inside the pair of brackets, I have B union C. So this becomes intersection. I have this pair of bracket. Instead of B, I put A, E, and F, and then I union it with E, F, and D. Okay? So I need to determine this set. But of course, this pair of brackets means that the priority is with this operation because I have two operations involved. Okay? So this means that I have to do this one first. So this means that I just copy and paste the first part that I am not going to touch. But then I ask you, what is the union of these two? So do you remember how to write the union? Union consists of all the elements that are at least in one of these sets. So if you remember what I said, when I want to write the union, I copy every element of the first one without any without being careful at all. I just write A, E, and F. And then when I want to append the elements of the second set, I have to be careful not to repeat any element. So E is already written, F is already written, so I have to add only D here. So that is the union of these two sets. And now the turn is for intersection. Intersection means those elements which are both in this set and that set simultaneously. And this is clear that A is one of them. E and F are the other ones. There is no more, yes? No, yeah, there is also more, yes? A, E, F, D. So these three. A, D, E, F. Okay, so I will give it a number 1. And then I calculate the left-hand side. Sorry, the right-hand side. But again, let me make it a little bit smaller. To the right-hand side is this set. So first you need to write it down. So I would write a pair of brackets, then I have the set A, so it becomes A, B, C, D, E, F. And then I have intersection with set B, which is A, E, F. And then I have union with A intersection C, which is again A, B, C, D, F. D, E, F. Intersection with C, which is E, F, and D. Okay. Now I can make it bigger now. So now here I have 3 operations, 2 intersections, 1 union. But these pair of brackets has the role to tell me which one has the priority. So this one should be done first. These 2 can be done in parallel. And then when I found the answers, I actually union them. So what happens here is this becomes equal. The intersection between these 2 is all of it actually. A, E, and F are in both of them. So it becomes A, E, and F. And then what is the intersection here is again all of them. It is E, F, D, yes? E, F, D. So then it becomes union E, F, D. And now if I union these 2 again, I write the first one, and then when I want to append, I need to only add D. Yes? But then if I put this as a number 2, then if I compare number 1 and number 2, I can immediately see that these 2 sets are the same. And I told you that, of course, the order is not important when it comes to equality of sets. So A, E, F, D, A, E, F, D. These are the only elements. So I would say that from 1 and 2, one can conclude that the left-hand side is equal to the right-hand side. So that is also one type of examples that you see in the book. Another type is that you can investigate equalities with Venn diagrams. Okay, so let me also, for example, check the validity of this one using the Venn diagram. Okay, so let me just give you this as an example. Check the validity of the previous theorem using a Venn diagram. Okay, so let me just again check the first one. So that was the question we want to check. So what was that? The first one, yes. A intersection B union C is equal to A intersection B union A intersection C. Okay, so this is what we want to check its validity. Yes?
What is a Venn diagram?
Now, these Venn diagrams are the diagrams that you have. For example, do you remember a rectangle for the universal set and circles inside? These are called Venn diagrams.
Okay, yeah, okay.
Yeah. So So how should we show that? In principle, of course, you see that there is nothing very special about these sets. We don't know anything about these sets. So we need to consider the most general case. The most general case means that they are mutually intersecting. Yes. So so let me make it a little bit bigger. Yes. So assume that this is the universal set. And for example, this set, let me call it set A. Let me choose another set, for example, this one to be B. And then this is, you see, I am drawing them in a way that they are intersecting because this is general case. If I draw them like this, it means that I am assuming that they are not intersecting at all. So it means that I am considering particular cases. So in general, if I don't know anything about sets, if you want to draw a Venn diagram for them, you need to respect this, that you need to consider the most general case, okay? Unless you have a good reason not to do that. For example, it might happen that in the problem itself, it is telling you that A and B are mutually, they are disjoint sets. So it means that you have to then draw them in this way, not intersecting at all. But when there is nothing given about those sets, draw them in this most general form. So let me just go to another color, so which might help. So here, let me choose this one a little bit. Let me choose this one. Okay, so for example, if I want to draw, so let me name them. I call this one set A, and then this one set B, and now I draw another set C. So for example, I draw it in a way that it intersects with these sets. So I will call this set C. Okay, and let me copy exactly another version of that. Copy, make them identical here. Okay, now here I, for example, write the left-hand side here, and here I will draw the right-hand side. And I want to convince myself there is no difference between the left-hand side and the right-hand side in these two diagrams. Of course, this is not a rigorous mathematical proof. The rigorous mathematical proof was the one that I did from mathematical logic and the definition of intersection and union. But this is a very good intuitive tool in our hand to convince ourselves about the equality of sets. Okay, so I don't know how to draw it. So let us consider it together here. I want to highlight this in the diagram on the left. So here I have B union C, and then I have A intersection. So I don't know. So let me see if this works in this way. So where is B union C? So I draw a border around that, and then you tell me that if you agree with me or not. So what I say that this is B union C. Whatever is inside this black border, this black line, is B union C. Do you agree with me? Is that clear? So what I am telling is that the whole region here is B union C. Do you agree with me?
Yes.
Okay, so that is I don't know how to draw it, but that is a good way to see it. But now I want to have the intersection, this blue circle, with this region inside this black line. I want to find those intersections. So let me change my color. Let me see if I have a good color here. Yeah, we can choose this one. So I want to find the intersection between the blue circle and the region inside this black line. So if you agree with me, this part that I am just hatching is actually that part. Yes? So this part is A intersection with the union. So this orange part is actually the left-hand side. Yes? Now I'll go to the right-hand side, the same diagram. Here I will have A intersection with B. So where is A intersection with B? Let me just highlight it here for you. This part is A intersection with B. And then where is A intersection with C? Here is A intersection with C. Yes? But then you see that if I union them, it becomes exactly this orange part. So this means that hopefully you are convinced that these are exactly the same thing. But I don't know how to draw it carefully here. So for example, I can have this one that I am hatching now. This part is A intersection with B. And if I change my color, for example, to this light green, this part, you see this part is not, but I'm also going inside here as well, yes? This is A intersection with C. And then if I union them, it is clear, let me draw a black border around what I have. So if I union them, I will get exactly this thing here. And that is exactly what you see here. So this is also one way to convince yourself that these two sets are equal, but of course this is not a rigorous way of dealing with sets. Any questions? So this is also one type of questions that you will see when you are doing exercises. Is that clear? Okay. Good.
Baba?
Yeah. Yes?
So the black line around B and C and on the left-hand side is not drawn in the right-hand side. Why? You only draw the orange.
No, because here I didn't exactly understood what you said. Let me just repeat here. What you see, this black line on the left-hand side is inside this black line that I am hatching now is B union C. Okay, remember it in your memory now. When I take the pen, it will disappear. And then I have A intersection with that part that disappeared. A is this part, yes? And B union C was this part, do you remember? Now, if I ask you where are the intersections are exactly these orange parts. So this orange part at the end is the answer to the left-hand side. You can just clean this black one if you don't like to. That was helping me to understand what's going on. Okay. Yes? And I did the same thing here. Again, this black one, I didn't know how to do it. If you want, I can hatch it with the orange again. But I was hopefully able to convince you that if you do this, again, you will get this area, inside this area, this region, in a different way. Yes, do you understand what I mean?
Yes.
Is there any question left or you're happy?
No, I'm happy, I understand.
Okay, good.
Yeah.
Okay, now let me give you some more interesting examples using this rule. Of course, the emphasis in this course is not being able to do this algebra. So the examples in the book are not very homogeneous. Some of them are harder and abstract, some of them are very easy. But anyway, this is mostly this is the algebra of sets. I will not emphasize on it very much in the exam, but at least you should be able to understand the simple ones. Okay, so let me give you some examples of this type as well before leaving this section. So example, simplify. A and B are sets. We don't know anything about them, but we just know that A and B are sets. And then we want to simplify. So, for example, number one, let me solve one of them at least for you so that you have enough experience. So you want to have A intersection A complement union B. Okay, so this is given to you. I don't know anything about set A and set B, but I have this combination. The point is that can I use the rules that I have learned for union and intersection to write this set in a more simplified form? This is the algebra of sets. Do you remember in algebra, an expression is given to you, and then you, for example, you have A plus B and A minus B. Can I write it as simpler? Yes, you can multiply them. It becomes A squared minus AB plus BA minus B squared. Then these two are gone, so you can write A squared minus B squared, yes? So, which is actually a simplified version of that one. So of course, those are the rules of algebra of numbers, but we also learned algebra of sets with the operations among the sets. So far, we have learned 3 of them. 2 of them, union and intersection, we also learned how to write the complement of a set. Now, I want to use these algebra to simplify this expression if possible. Today, we just learned, first of all, you see that I have a intersection here, and then I have a union. So it has the correct form of distributive law, one of them, yes? So I will take this A union and I will distribute it inside this pair of brackets. So, but you need to know how to write it. So the one that I am writing with green is the solution. So this becomes A intersection with A complement. If you have problems, please let me know. I am just using the rule. Union A intersection with B. Everyone understands why this is correct? Based on exactly this rule. Yes, you see here, if you see A is just the same A, but here A complement is playing the role of this set, and B is playing the role of this set. So I am using this version of distributive law to be able to distribute A intersection over this union. Is that clear? Good. Now, I hope that you haven't forgotten, because these are not something that you really need a formula sheet for. If you just understand what's the meaning of complement, intersection, and union, you can do a lot of things. So now, do you remember, or can you tell me what is this one? A intersection, A complement.
Empty set.
Empty set, exactly. You see, so this is the empty set. So I will continue one step more, and I will write the empty set, but then I have to copy and paste everything after that, because there is nothing I can write for A intersection B. I don't have any relations between A and B, so I cannot do anything with that. So I have to copy and paste. So I have a union, I have A intersection B. Do you think I can simplify this a little bit more?
Yes.
Yes, what's the answer?
A intersection B.
Yes, because we know that any set unioned with the empty set is the set itself. So the answer to this is just A intersection B. But I cannot go any further. But at least it is a good progress. A intersection B is much simpler. Not much, but it is simpler than this one. Okay, so this is the algebra of sets. Somehow I want you to learn that. Okay, let me give you another example. Number 2. What do you think here is? Can I simplify this expression? A intersection B union A intersection B complement. Can I simplify this? I just want to wait a little bit for you. Can you tell me how to start?
maybe we factorize it.
Exactly. Can you tell me factor what?
Factor out, I think, A.
Yes, A, you see A intersection is in common. So exactly like, let me write A dot B plus A dot B prime, yes? If you had this situation, you can factor A dot out, and then you write B plus B prime, any numbers, yes? It's more or less the same thing, but in numbers, we have only this formula, but for sets, both of them are distributive over the other one. Okay, so here, as Alex told, I will take A intersection out, then I have to put a pair of brackets in front. I pulled A intersection out. What is left from this is B. I pulled A intersection out. What is left from this one is B complement. And then the operation between these two, when I pull this out, B union B complement is left. So this is B union B complement. So you see, it is actually a little bit simpler, but I can go even further. So what is this one now? What can I write instead of this, a pair of brackets?
The universal set.
The universal set. So this becomes A, the intersection with the universal set. But still I can go further. What is this one now?
Just A.
Just A, yes? These are the rules that we had before. So you see, I was able, even without knowing anything about the elements inside these sets, that's a good thing to do, yes? This combination is nothing except A itself. So it is much, much simpler to work with A than working with this combination. So this is algebra of sets. Is that clear? I have also one more exercise here for you, but I will pause the video and wait for you. It's a little bit harder, but not that hard. So I want to wait a little bit for you to simplify this for me. So A intersection A complement union B, and then I have union, then I have B intersection A complement union B complement. Okay. So I pause the video, wait for you for, I think, 3 or 4 minutes. It's enough. Then we continue.
And bye-bye.
Okay. The way that I did it myself, I was concentrating on doing this part and this part using distributive laws separately. And then when I found the simpler answers to each one of them, then I union it. Okay, so what I am doing is, let me write on the line below. Yeah, so what I do here, I distribute this inside this pair of brackets. So it becomes A intersection A complement. Then I have the union A intersection with B. What I have written here is just the answer to the first pair. Okay. And then I have this union here. So I put the union. And I will do the same thing in the second pair of brackets by distributing this here and here. Yes, so then what happens, it becomes B intersection A complement. Then I have union B intersection with B complement. Please, if you have any questions, interrupt me, okay? I cannot see the chat window if you write something. Here, then I can continue, and instead of this, I can write the empty set. I can write the empty set for this one as well. Now, let me write this. This, if you want to write it in the exam, you need to write all these details. So this is the empty set, and then I have union, the rest of this. And then I have union in B intersection A complement. I cannot write something for this. But this, the second one is also the empty set. But now here I interpret it in this way. I have some set, whatever it is, it doesn't matter. I am union it with the empty set. So it becomes the set itself. And then I don't need to write this extra pair of brackets anymore, because the role of this pair of brackets was to prioritize this operation. And when this operation is done, I don't need that anymore. And then after that, I have union. The same idea is again the same here. So I am unioning a set with the empty set. It becomes the set itself. But again, you see, I know that I can commute. Intersection. So it doesn't matter if I have A intersection with B or B intersection with A. The reason that I am use commutativity here is because I want to have B intersection on the same side, of course. And then B intersection is in common. I can use the same technique. I can take it out. And then what is left for me from the first set is A, from the first pair of brackets is A. From the second pair is a complement, and the operation between these two should be a union. But then again, there is a rule for this. A union, A complement is the universal set, so it becomes B intersection, the universal set, and B intersection, any set intersection with the universal set is the set itself. So this big expression is nothing except B itself. So you see that if you learn the algebra of sets, you can also manipulate a little bit more complicated set expressions. Is that clear?
Yes.
Okay. Now, there is also a delicate point here. There is another theorem. It's called absorption laws. So let me also talk about that. You shouldn't get confused. That's also good to know. So let me write theorem first. Okay, so let me write this is optional. If you don't mind, you can skip that. Let A and B be sets. Yes, then we have two absorption laws. So one of them is this: A intersection, again A union B. Yes. So you see, it is very similar to distributive law, but in distributive law, I have three different sets: A intersection, B union C. Okay, but here one of these sets is being repeated. Absorption laws tells you that if you have this combination, the answer is simply the one which is repeated. It can be the other way around. It can be that the union is first and the intersection is coming after that. Again, the answer is A itself. You might say that this is exaggeration, why we need another law, because I can use distribution law to prove that. I just want to tell you, I write something and then I clean it. This is the reason that this deserve to be another theorem, is that even though it seems like distribution law, but distribution law is not capable of giving you this answer. It will not give you a wrong answer. It will always give you a correct answer, because that's also a law, but it is not capable to simplify this up to this very simple point. That's my goal. So let me just do it. For example, let me write with some color and then I will clean it. You might say that, okay, let me use distributive law here. Can I use distributive law? The answer is yes. I have one union, I have intersection, I have union, so I can distribute it in. When I distribute it in, it becomes A intersection A union A intersection B. And then we know that if I ask you what is A intersection A, the answer is clear. It becomes A itself. If you remember, we had this property before. And then I have A union B. But you see, it is not wrong. This is equal to this. So what is distribution law is telling to me is that this combination is equal to this combination, which of course is true. But absorption law tells me more, tells me that this is equal to A and this is equal to A. And of course, if both of them are equal to A, they are also equal to each other. Distribution law is capable of showing the equality between these two without showing you what is the simplified version of them. And if you insist to use distribution law once more, it would become a cyclic argument. You see, if I distribute A union inside, again, it becomes A union A, intersection A union B, but then this part is A, this becomes A intersection A union B, which actually we returned to itself. And we showed that this set is equal to itself. So yeah, good morning, yes, a set is equal to itself. Okay, so this is why this deserves another name. And so let me clean this one. We don't need it anymore. But let me, as an exercise, to prove this one for you. Okay. So proof. Of course, you can also use Venn diagram to convince yourself. By the way, for example, this can be given in the exam, even though I have written optional, and I can ask you use a Venn diagram to motivate this. This is possible, okay? So for example, let me prove number one, you can prove the other one yourself. So A intersection A union B, I can write it in this way. Of course, I can have two proofs, but let me just do this one. Instead of A, I write A union empty, and then I can write A union B. First of all, let me see that this is correct or not. I copied this I copied this part here, but instead of A, I wrote A union the empty set, which is correct, yes, because A union the empty set is the set A itself. But why this is useful? The reason is that I can see now that A union is in common in both pair of brackets, so I can use the distributive law in the opposite direction, means factorizing, yes, somehow. So I can factor A union out, and what is left from this is taken out, so empty is left. This is taken out, so B is left, and the operation between them is the intersection. So this becomes empty intersection with B. So you see, I am using again the distribution law, but in a wise way. Yes, but now why this is working? Because if I ask you what is this, you can immediately answer this is the empty set. So this becomes A union the empty set. And now if I ask you what is this one, you can immediately answer this is A. So it means that I started from the left-hand side and I was able to show that this is equal to the right-hand side. Okay, you can prove the other one similarly that this is the case. Another way, let me just talk about it orally. Why this is easy to show that this is immediately equal to A? Because if I ask you what is the relation between these two sets from subset points of view, do you remember? We learned that this set is always a subset of the union. And then do you remember I told you that if a set is a subset of another set, if I ask about the intersection between these two, do you remember what is the answer? If I give you this piece of information and I ask you about this intersection, you can immediately answer. What is the answer? Do you remember?
It's O, right? No, wait, this is a lesser one. This is a smaller one. It's the box.
The smaller one. This is the box, yes? And now I am telling you that I have two sets. So let me just take this one, the box, and then this one, the circle. So am I sure that the box is a subset of the circle? Yes, because of the properties of the union that we studied before. Now that I know the box is a subset of the circle, if I ask you what is the intersection between these two, you just answered. It is the smaller one, which is the box. Yes? So unfortunately, it disappeared. Okay, so let me just repeat it here. So A intersection A union B. I want to calculate this. I will take this one as my circle, and I will take this one as my box. But I know that box is a subset of circle. So if I ask you what is the intersection between these two, you immediately answer it's the smaller one. Okay? But what is the smaller one? The smaller one is A, so the answer is 8. So that is also a complete rigorous mathematical proof. But I think it needs to write it in words, but here you really don't need to write anything in words. So this is why I prefer to write it in this way. So this is absorption law. So this one is also optional, but let me write an example for you. Optional. Okay, simplify. Okay, how should I simplify these? For example, number 1, A union A intersection B, and then union A complement intersection A complement union B complement. Okay, so assume that I want to simplify this. Let me just do it myself because I want to teach the other parts. So this is the optional part. So can you tell me what's the answer to the first pair according to this absorption law?
A.
It is A. Yes, because I have union, I have intersection, but one set repeats itself. According to absorption law, the answer is the repeated set. So if I want to write this, I would immediately write it A. I don't need to calculate anything at all for this part. But now, can you tell me what's the answer to the second pair?
A complement.
It's A complement. Yes, this is very important to realize. You see, I have intersection, I have union, but one set is repeating itself in this combination. According to the absorption law, the whole expression is the repeated set, which is A complement. And then I have union, and this is A complement. So this becomes union, A complement. But we know that what's the answer? A union, A complement is just a universal set. Yes? What do you think about this one? Number 2, and that I will go to the lesson in the book. So A intersection A union B intersection A complement. Can you immediately answer what is the answer here? No calculation is needed.
Is it A?
It is A. Can you just elaborate why?
Well, I can imagine B intersection A complement to be another letter, for
box.
example,
Yes,
C.
exactly. So what he is saying is that this one, for example, you can assume this is capital B. And then you have A intersection A union capital B. But this is absorption law, yes? Intersection union, a set is repeating itself, so the answer is immediately A. So you see, no calculation is needed, and the answer to this combination is A. Of course, if you want, you can use distribution law and do calculations more and more. Of course, at the end, you will get A, but this is much easier to understand. Okay? So now let me find this optional part is finished. There are, I will give you another theorem. It is mentioned in the level 3 problems in the book, and there they have asked you to prove them mathematically, but they haven't given it a name because, as I told you, that they don't probably expect you to learn these things in a structured way. But if you want to know them as a structured way, these are theorems that you need to know them, and if you want, you can use them. And these laws are called Demorgan laws, okay? So let me write a theorem here. So this is a level 3 problem in the book, okay? And this Demorgan is the name of the guy who invented this, Demorgan Laws. Okay, so I would say let A and B be sets. This tells you how to find the complement of a union or the complement of an intersection, okay? So there are two laws. Number one, this tells you that if you have the intersection of two sets, and then you are interested in finding the complement of the result, you can do like this. You can take the complement of the first one. You can also take the complement of the second one. But if you write intersection, that is wrong. The intersection will change to union and the other way around. So number two is this one. What happens if I have the union of two sets and I want to find the complement of the union? I can complement the first one, complement the second one, but I need to change union to intersection. These two very important laws are called Demorgan Laws, okay? Because this is a level 3 problem in the book, so let me prove one of them at least for you, and you can do the other one yourself, okay? So whenever you want to prove something rigorously, there is only one way. You see, this is one set, this is another set. We are claiming that these two sets are equal, and we want to show that is true. Whenever I have two sets, I want to show that these are equal. There is only one way to do that. Take an element here, arbitrary element on the left-hand side, and show that that element is in the right-hand side and the other way around. This is the standard trick when you want to prove this. So let me write proof. I will do number one. You can do number two yourself, for example. Okay, so what should I do? I would say let X be an element in this set. We show that X also belongs to the right-hand side and the other way around. Okay, now help me to do this, for example. So I take X in A intersection B complement. Can you tell me, based on your previous knowledge, what is the logical consequence of this assumption?
X is in both A and B.
No, at least not directly. So what you know is that X belongs to a complement. What is a logical consequence of that? What was the meaning of being in a complement set? Do you remember?
That X is not part of A intersection B.
Exactly. So that is the logical consequence of this. When you say that X belongs to the complement of a set, it is 100% guaranteed it is not in the set itself. So it means that this does not belong to the intersection. So far, I hope that if you have any questions, please interrupt me. Now, can you tell me what is the logical consequence of this statement that an element is not in the intersection? Do you remember I talked about these before? The reason because I was looking ahead of me here. So when you say that X does not belong to the intersection, what can I conclude from this?
It belongs to a union.
May you speak louder, please?
It belongs to a union.
No, I didn't hear what you say. X belongs, what?
No, I said it belongs to a union.
No, you cannot immediately jump from this. Why do you say so? Because, for example, let me draw a diagram for you. For example, if this is A, this is B, yes, and this is U. What I say here, I am telling you that x does not belong to the intersection. So what I know is that x is not here. This is forbidden for x. Of course, it might be here, it might be here, but it also might be here. So I cannot say that it is in the union. Do you understand me?
Yes.
If it is here, you are right, it is in the union. If it is here, you are right, it is in the union. But it might happen that this is here. If this is there, then it is not in the union. So I cannot jump from here to here. Any other opinions?
It means that X either doesn't belong to A or it doesn't belong to B.
Exactly. So this means that X does not belong to A or X does not belong to B. Why is that? Because if X belongs to both of them, based on the definition of intersection, it will also belongs to the intersection. But now you are telling me that X does not belong to the intersection. It means that at least it is not either in A or not in B. So let me just correct myself. When you say that X does not belong to the intersection, it means that it is not at least in one of them. Because if it is in both of them, it has to be in the intersection as well. But now you are saying that it is not in the intersection, so it means that at least it is not in A or not in B. Is that understandable for everyone?
Yes.
Okay. And now tell me, when you know that X does not belong to A, where does it belong to?
A complement.
A complement. And the same for B. When you say that X does not belong to A, I can conclude that, okay, X belongs to its complement. Or when you say that X does not belong to B, I can also conclude that X belongs to its complement. But now look, you are telling me that this element either belongs to this set or belongs to that set. What can I conclude? Can you tell me based on the definition of the union now?
X belongs to the union of A complement and B complement.
Exactly. So X belongs to the union of A complement and B complement. So we are done. Yes. We were supposed to take an element from the left-hand side set and show that the same element belongs to the right-hand side set. But the problem is not finished because we also need to do the other way around. And usually my experience is that most of them you can just reverse the direction of the arrows, okay? But you need to convince yourself, of course, is this arrow reversible? Yes, because if you tell me that X belongs to the union, I can immediately conclude that either it is in the first one or in the second one. So this means that this is valid. And then can I go the other one as well? Yes, because when you tell me that X belongs to A complement, I am on the safe side to conclude that X does not belong to A itself. The same for B. Can I go the other way? Yes. Here I can also reverse this arrow because you are telling me either X is not in A or X is not in B. So definitely it is not in the intersection. Yes. And then now you are telling me that X does not belong to some set. I am on the safe side if I conclude that, okay, that X belongs to its complement. So it means that all these arrows are reversible. So it means that if I choose an element here going in this direction, I can show that that element also belongs to the left-hand side, and it means that this is equal. I really recommend you, this is a level 2 problem, try to solve this one yourself as an exercise. Any questions? Okay. Let me give you an example that you can use this Demorgan laws. So Let me see which one is better. Let me give one simple one and one a little bit harder. So example, simplify. So number one, A union B intersection A complement union B complement. Yeah, think a little bit about this when I am writing the other one. Yeah, I can pause the video so that you can think about it. Okay, do you have any answer for the first one?
I think it's the empty set.
Yes. Can you tell me how did you get it?
I've used the fact that complementarity is distributed.
Let me see if I have written it in the correct way. I think I have. I don't see it myself now. I was thinking that this is simple, but you say that this is empty set, yes? Because my goal was to make it simple. I'm not completely sure about that this is the empty set. My intention, I think my intention was not to make it so hard, but how did you come to the answer that this is empty? Might be I am not seeing something. Can you just say me how this is the empty set?
Well, I thought that I could move the complements in the second brackets. I could move them out of the brackets.
Yes.
Look, that
was my intention, but unfortunately, I think I wrote something wrong. Sorry for that. Yes, you are right. But if I have A complement union B complement, if I want to move this complement out, I can write A, B, I can put complement here, but what should I write?
You would have to change it from.
Yes, I have to change. So that is why probably I made a mistake when I was writing it. It might happen that this is also the empty set, I don't know, but that was not my intention. So if you don't mind, let me just clean and fix it. And that was the point, yes. So this one should be intersection here. Sorry. That was what I mean. Okay, so here now what you are saying is correct, because I can write A intersection B as itself, and then I can put this intersection. But according to the Demorgan laws, I can write A intersection B and then complements. So what you see, instead of this, I am putting this one, but the price that I need to pay to bring this complement out of the pair of brackets is to change the union to intersection. That is the essence of this Demorgan's law, yes? And now this answer is immediately empty, as you said. Why? Because who cares about the name? This is a set, and that is the same set complement. So if I have a set intersection with its own complement, no matter what is inside this box, the answer is the empty set. And now this is correct. Sorry, that was my bad. Okay, now let me just do this one quickly because we are running out of time. And then if you have any questions, you can just ask me again. So here, I use the Demorgan law here to simplify this. So Demorgan law tells me that this will go inside. So I need to write A complement, but I need to be careful. This intersection should be changed to union, and then I will have B complement, another complement, yes? This is the Demorgan law applied here. I will use the Demorgan law here again. So this becomes B complement, then this becomes union, and then that becomes complement, complement. And then, of course, I have, if you want to, you can write this one. Let us keep it for the time being to see if we need it. But then we have a rule that we know that complement of complement is the set itself. So it becomes A complement union B. And then I have union. Here is B complement. Here is B complement union A. And then I have union A intersection B complement. But you see, I don't need these pair of brackets anymore because all the operations that you see here are union operations. And then we know that union is commutative and associative. So it means that if I want, I can interchange the places of any of them. I can group them in any order that I want to. Of course, it would be beneficial if I write A complement union A together because I have a formula for that. And then I can write B union B complement together because I have a formula for that. And let me copy and paste the last part. But if I ask you what is this, the answer is U. What is this one? The answer is U. So this becomes universal set union with the universal set. And then I have union with A intersection B complement. But the universal set union universal set is the universal set union with this set. And the answer, no matter what the set here is, the answer is the universal set. So the simplified version of this is the universal set. Of course, I'm not saying that this is the only way of solving. If you have logically done something else, but you got the correct answer in that way, that's also accepted. So there are two topics left from this set theory. One of them is the subtraction between two sets. That is another operation between two sets. And then emphasis on the Venn diagram for problem solving. These are the only parts left. I think we can finish it in one session, or at least at most 1.5 sessions. I will, of course, write on a Schoolsoft. Probably this lesson is again no new pages. Yes, you can just work on the problems that I have already written on a Schoolsoft. Any questions?
No.
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 So let me